Welcome to module 9 of object oriented analysis and design. We have been discussing about elements of object models. We have noted in the last module that there are 4 major elements of object models and 3 minor elements. Of the 4 major elements, we have already discussed about abstraction and encapsulation. We have seen that abstraction is widely used to identify the key concepts in the system, and it relates to primarily design formalization, whereas encapsulation has to deal more with the implementation aspects of the system, which encapsulates or packages the implementation and puts it away from the public view, giving only a limited required view of contractual interface to the users. And we have seen through different examples as to how encapsulation and abstraction interplay between themselves. Building on further, we will in this module take a look into the other 2 essential characteristics of object models, namely modularity and hierarchy. This is the outline. We will present a quick recap and then discuss the specifics of modularity and hierarchy. So, this is just to remind you that these are the different elements of object models that we are discussing in this series of modules, and we will now focus on modularity. So, modularity has to do significantly in the way a program or the code of the software, the data of the software, how it is organized. So, modularity is about partitioning a program into individual components, and we want to do this, we want to make modular designs so that we can again manage complexity. So, it is yet another aspect of system management, which addresses the original set of issues we had raised about software, about the inherent complexity of software and the inherent inability of human beings to deal with more than a few semantic elements in any design or any implementation. A typical characteristic of modular designs or modules themselves would be that they compile separately, though in cases they could compile together, and obviously there is interconnections between the modules. So, we will start with an example. So, this is please do not get worried about the clutter of this diagram, it is intentional. We are just trying to show that if you are dealing with the design of a machine learning system, then this is the kind of different components that you need to deal with, and these different sets shown in different colors show the different modules. So, I will quickly take a work around the modules. So, one module is data transformation, where what we need to do is in whatever form we are getting the data for machine learning, we have to transform them, represent them into different standard forms of linear manifolds or vector manifolds and so on. So, all components relating to these transformation tasks is put together in the data transformation module. A second module or another module is structured prediction, which talks about given a certain pattern of data, what can you how can you infer a predictable model for that. You will often use Markov random fields for that or different other ways of doing structured prediction. Again, the specifics of this are in the domain of machine learning. So, it is not expected that you will understand it. that is also not the requirement. I am just trying to show that these are the different kinds of module that a complex system can have. We will have a separate module for clustering, which when we do not know, given the data, how many different categories or subcategories or classes it belongs to, we perform clustering to decide on what is a good set of classes. We will have a classification module, which given the set of classes and given a test data can decide which of the classes it does belong to using different machine learning algorithms. And then there is a regression module, which checks based on the different test cases as to whether it has been correctly classified or the classification has actually regressed, in that there is some errors in the classification. And finally, all these different modules actually interplay between themselves. So, this particular area, if you see on different sides, I am showing the different modules that you we have already shown, the data transformation, the structured prediction, the clustering, classification, regression. So, all of these are the different modules that you have clubbed your code into, but then this together becomes a system when you have the interconnection between modules. So, when we talk about modularity, one is grouping, partitioning the program codes into interrelated, semantically interrelated set of files and data. At the same time, there are certain interconnection parts. For example, here if you look into all these different subcomponents, their task is to basically create the interactions between different modules, and this will typically be the view of any complex system when it is modularized. This was just to give you a glimpse of what kind of complexity a system will actually involve, and how modularization can reduce some of this complexity. So, you can very well understand that if you think back about the original system, we just looked at a clutter. Compared to that, when you take each and every module, it is much easier to handle that, and this can again go in an hierarchical manner. A module can be again sub-modularized into smaller modules and so on, and we will look into some of those principles. So, to set the target, there are certain specific objectives of modularization. So, let us look into them one by one. One is the decomposition, that is, we want to, given the whole set of codes files, we want to organize them in terms of modules, in terms of related groups in a systematic manner. So, that what it meant by systematic manner is we only put together those part of the program or those part of the code into one module, which has some kind of well defined functionality. We just do not arbitrarily, if there are 100 program files, we will not arbitrarily put 17 of them into one module, but we will put them together in a way, so that together they either represent a set of concrete concepts or they provide certain algorithmic functionality and so on. So, modularity of decomposition is a key area. The second is composability, that is, as we divide the system into smaller modules, every module into sub modules and so on, we should be able to reconstruct it back. That is, we should be able to take smaller modules and put them together into a bigger module. So, the way it will help is, if we have similar functionality in 2 or more areas of the program, then we can have a single sub module which can be reused, composed into other modules and increase the reusability. So, modularity significantly increases the reusability. If you just want to think of in terms of the conventional C programming that many of you may be familiar with, you will find that we often use standard library, right. You know that C uses standard library, right. And in standard library, what do? You include different standard library headers. We say this is, we have stdio.h, we have hash include math.h. We have hash include stdlib.h and so on. Now, all of these header files necessarily have a set of function headers, because you are talking about C programming. So, there is no class, but you can still see the explicit use of modularity, very organized use of modularity. So, what are we doing? Why do we need to have all these different header files? Because I mean, what could have been the other alternative? I could have had a standard library.h include all the function headers, but we do not do that. So, what we have done? We have done a specific decomposition and composability. So, when we talk about stdio.h, we have put together all those function headers like printf header, scanf header, fprintf header, fscanf header and so on, which relate to some kind of input output mechanism. But when we will have to deal with different mathematical operations like computing the tangent of an angle, the tan function or the arctan function or the square root function, we will have a separate header file which puts them together. So, the way this will easily demonstrate that while decomposing all different standard header files or all different standard functions that you want to provide to a C programmer, you do not provide them as flat. You decompose them into functionally congruent. These actually never interact also between the printf does not interact with scanf, scanf does not interact with fprintf, and certainly arctan does not interact with sine, but you still conceptually put them together, because with that it becomes much easier for the user to use that module. So, the composability becomes easier. User wants to build up a program, all that she needs to think of is, am I doing an input IO here, then I must include stdio.h. Am I doing something which is relating to say memory allocation and deallocation, I must use standard lib.h and so on and so forth. So, this is just a simple example relating to basic programming that shows that modularity is a key requirement, is a key tool in terms of organizing the code better, in terms of providing good decomposition, good composability. And the consequence of that, if when we have been able to do this well, then the other objective that you meet is modular understandability. So, as I said that if I want to do input output, all that I will need to do is include stdio.h. So, this is the understandability, that is, I understand, I have a semantic meaning for that module, even though as I said the different components of that module, different functions do not interact between them, but there is a conceptual boundary which says that all input output operations would be here. So, I can understand the module as a kind of unit which makes it easy to use and which makes it also easy to change in case I need to make some changes. The fourth objective is modular continuity. Modular continuity is little bit more in depth. What we want to do is we want to divide the system in such modules, so that if in future we need to make some changes, and changes can be because of different reasons. For example, the changes could be simple bug fixes, that there are some issues in the code and I need to fix that, correct that. The changes could be due to change in specification, the changes could be due to change in the business process and so on. So, I would like to, we should be creating modules in a way, so that when some change is required, then that change should not go across multiple different modules. The change should be limited to one module or should be limited to very small number of modules. So, if the modularization is not very proper, then changes will spill across different modules. For example, if I had split the math.h set of headers into two different modules, or if I would have clubbed math.h with stdio.h, then any change in the numerical algorithm to compute different trigonometric functions would have spilled across modules. So, this will reduce in a way, this will reduce what is most important is it will reduce the side effect, that is change of one module impacting the other, and certainly related to that objective is modular protection, which say that the errors should be localized, that is if I come across a error, say I come across a divide by 0 error, then it should be localized to math.h. If I come across a memory allocation failure error, it should be limited to memory.h and so on. So, these are the typical objectives which should be kept in mind in performing a modularization of the code, performing the modularization of the design that you are given to deal with. Now, certainly in life no lunch is free. So, when you engage in modularization, try to meet these objectives, then you often come across challenges. For example, given a general system, it is not often easy to decompose it in terms of smaller modules. Often it needs quite in-depth study of the system, understanding of that, experience of design, and often the use of other elements of object models, like identifying what are the abstract concepts, what are the possible encapsulations, even what is the hierarchy if something is existing, and so on. So, it is not always an easy trivial task. It is not always just that you decide on which files that you can put in one module or the other. Even deciding which functions you put in different files, which headers you put in header files, which class definitions you put in different files, all these go in depth in deciding how well the modularization is happening. And keep in mind that if the modularization is arbitrary, then often it turns out to be actually more disastrous. It is often worse than not modularizing at all, because you are drawing boundaries which are not aligned with the design boundaries of abstraction and encapsulation that you are already emphasizing. So, modularization should follow the semantic grouping of common and interrelated functionality. So, please note these points, that it should follow the semantic grouping, that meaning wise they should be similar, they should be interrelated. And what should be interrelated are common items, common functionalities, interrelated functionalities. Interrelated functionalities will make sure, for example, I will again go back to the example of stdio.h. Think about the printf function. So, it is an input output function which C programmers will often use. So, you have put it in the stdio.h. Now, there are functions which some of you may know, functions like read, some functions like write, which can also be used for input output, but they are at a different level of detail. They do more like binary data read write and so on. Now, if you put the printf into one module, one header file, and put read write into a different, then you will find that you will often have a lot of interaction across these two modules, because printf will never get implemented by itself. Printf will regularly use write operations. Write operations will use other kinds of input functions. There are functions called input and so on. There are functions called fwrite and so on. So, it is the commonality and interrelationship of functionality is a major clue by which you should be doing the modularization. In terms of challenges, I have just tried to describe some more systems. So, you can consider a distributed system which has many processors, and you have several messages going across these processors, hundreds of different kinds of messages. Now, the question is what should you modularize? Should you modularize, and since every module must be as independent as possible, you will put every module's required message types within that module, you can do that. But if you do that, then often you will have quite a poor design, because now since every module has its own message structure, a user who has to deal with these messages will not be able to deal with them without knowing in which module what structure exists. Documentation would become difficult, it will become really difficult to maintain. So, there are certain aspects like when you are putting them all together, then certainly you are kind of adhering to better encapsulation, because you said that well this kind of message relates to this module. So, let me put it inside that, you are hiding everything, but too much of hiding could actually impact the modularization a lot more. It could backfire, because now you do not know what are the different messages that need to go across, what are their formats and so on. So, you will need to strike a balance. You will possibly strike a balance by doing a different modularization, where you could identify that, well, since there are several kinds of messages, so why not create a module which actually deals with messages and provide interfaces which different modules can use based on what kind of messages they need. We will see more of that, but this is just a glimpse of what could be the possible challenges that we will come across. So, in this background, to keep to the objectives of modularization, we often talk about intelligent modularization. That is, these are some of the thumb rules rather, or some of the basic guidelines that you may follow to achieve the objectives better. Is one is that is why I have just highlighted the keywords in this. I am sorry, this got changed. The highlights the keywords, that is group logically related abstraction. You already have abstraction in the system. So, in a module you should typically, now naturally one extreme is every abstraction you put into a different module. That may give you a lot more fractured modularization, which will have lot of interactions. So, your modules will be simple, but you will have so much of interactions. You just recall the example I showed with the machine learning system, that the interaction part has to be also manageable complexity. So, instead of just putting every abstraction into a separate module, you will try to group them into logically related abstractions. So, abstractions of input output operations should lead to one module, abstraction of mathematical modeling should lead to another module, abstractions of system related operations should give you stdlib.h and so on. And as you do that, then what you try to achieve is minimize dependency amongst modules. So, this should be now clear, that if I logically group logical abstractions into module more, then certainly I will need to go across modules much less, only when I go across modules only when I need to achieve a higher level of functionality. And both of these, logical grouping and minimization of dependency across modules, will make every module simple enough to understand, and that would be a key idea. Simplicity should be a key idea of modularization, because recall that why are we modularizing? Because we want to contain the complexity. The complexity is too high, and we want to make we are doing all this to make things simpler, leveraging the notions, the vocabulary of the problem domain. I will frequently go back to that, leveraging the abstraction that I have already created, leveraging the possible encapsulations that we have, and finally, the modules must be simple. Final but overriding of the intelligent modularization principle is the ease of change. Even though whenever we do a design, when we start doing an implementation, start organizing the code, we are confident that we are doing a correct job, but the experience shows that for different limitations of the human mind, of the system, and of the business scenario, change is an inevitable, unavoidable reality of software development, of system design and implementation. So, ease of change must be always kept in mind, that is, we should organize the modules intelligently enough, so that some changes in one module should impact least number of other modules and so on. So, with these principles, we will regularly go ahead and look at different modules. There are some references to the earlier examples, the hypodronic gardening system. So, suppose we want to build up an automation system, which we started discussing, and certainly some of the key abstractions that we have seen include growing plan, that is, these are different strategies to be imbibed by the system to grow different varieties of plants, the user interface. So, these are some of the key abstractions that you would already have from the analysis of the abstraction of the system. So, it will be quite logical to create modules for growing plan. So, in the growing plan module, you may have a growing plan for fruits, a growing plan for grains and so on. It will be possibly good to put these all together, and this is what will relate to have grouping the interrelated abstractions together. It will relate to simplicity. It will make sure that you have it is much easier to change, because a fruit growing plan, change in the fruit growing plan will impact possibly the general growing plan strategies and so on. On the other hand, if all the user interface functionalities that you have, it would certainly be better to put them together into a single separate module. So, with this what we have seen is, we have seen the introduction of modularity as a major element for object models. We will stop here and next take up the hierarchy.